Alright, so in this lecture we're going to continue on with our discussion of the stress tensor. We're going to look at principal stresses, how they're defined, and some things that come out of that. Subsequent to this, we'll take a look at octahedral stresses and then Moore's circle. Okay. So we've shown the Cauchy tetrahedron previously, and if we wanted to, we could put things on a cube and have a cube here with the different stress components in it. These are only on the front sides that we can see. There are also stresses on the back sides as well. Some textbooks will kind of start with this instead of the Cauchy tetrahedron, but I kind of went the other way around, explained the tetrahedron, and now we can draw this cube. Now these stress components that I've shown on this directions are projections of the particular traction vector on each of those three faces. So I have a traction vector that's off in this direction. That will be the traction vector T1, not on the oblique face, but on the face that's perpendicular to one axis. And by dotting that traction vector with the E hat 1, 2, and 3 directions, I can get sigma 1, 1, sigma 1, 2, and sigma 1, 3. Now that we've shown that the stress tensor is symmetric, this stress component here and this one right there are the same. Perpendicular shearing stresses are going to be equal. So we have unique stress components. Now the normal stress term, sigma 1, 1, sigma 2, 2, sigma 3, 3, and the shearing stress terms, sigma 1, 2, sigma 1, 3, and sigma 2, 3. Now if we go back and look at the tetrahedron, we have that oblique face and we have the traction vector that has components of its own that line up with the 1, 2, and 3 direction, T1, T2, and T3. Now we're going to define principal stresses. Be defined as the stresses on planes with zero shear stress. In other words, for sigma ij, where I is not equal to j, those components will be equal to 0. We'll show that this is an eigenvalue problem, but one way to kind of think of this is if you take your fingers and put them into a triad. If you rotate that triad and rotate this cube in such a way that these shearing terms vanish, then you will have a principal stress state. Now in general, traction vector components on a plane are given by sigma ij in j when we are in the principal directions. The 1, 2 and the 2, 3 terms will go to 0. Then the traction vector components will be equal to some principal stress, call that sigma sub p, times ni. Okay. So the reason why is that if we were to expand the ti term out, we had sigma 1, 2, let's do it this way. Sigma 1, 1 in 1 plus sigma 1, 2 in 2 plus sigma 1, 3 in 3. This would be for I is equal to 1. This term would go away, and this term would go away because we're in the principal directions, and we're left with the sigma 1, 1 in 1. If we chose the 2, then we'd be left with sigma 2, 2 in 2. But in general, we're left with some scalar value of stress times the in with the component in the same direction as our free index here. So that's why we're calling it sigma p in I. Right, so writing that down again, like the T1 would be a sigma p in 1. We can get a similar equation for the 2 and the 3 components of that traction vector. And there are 3 scalar values of stress that satisfy this. They do not have to be unique, and they could be 0, but we could have 3 different values, a different value or the same value or 0 on each of the 3 different planes. Another way to say this then is that our sigma ij in j, traction vector component, is equal to some scalar times ni for some special choice of n. If we pick the right direction, then this will happen. And that sigma p could be sigma p1, 2, or 3. So if we work with this equation just a little bit, we can put both terms on one side. And we're going to do a little trick right here. It may not be completely obvious at first, but it works out. We have an n sub I right here. We could have thought of that as coming from an n sub j with a Kronecker delta acting on it. So this second term here would be sigma p. We can put in here Kronecker delta ij in j equal to 0. And remember, the Kronecker delta can act as a replacement operator on indices. So this is true. This will reduce down to ni. But the reason why I want to do that is now I have an nj common to both of these terms. And so I can pull that out to the side and write as sigma ij minus sigma p, Kronecker delta ij in j is equal to 0. In direct notation, I have the stress tensor sigma minus a scalar sigma p. The Kronecker delta can be represented as the representation of the identity tensor I acting on some unit normal is equal to n. This is an eigenvalue problem. As I mentioned when we went over stress, when I went over strain, the strain problem, you can set that up as a maximal problem on a reciprocal strain ellipsoid, the dimensions of that. We went through quite a bit of contortions to get that set up that way. Finally, I said, well, read it in the book. I usually assign that as a take-home midterm problem or something like that. Well, if we use as a definition for principal stresses as being normal stresses for which the corresponding shearing stresses are 0 in those directions, then the eigenvalue problem pops out of here very easily. Now, for this eigenvalue problem, there are 2 ways to make the statement true. There's a tensor over here on this side, a vector over here on this side. There are 2 ways to make the statement true. Either this tensor is the 0 tensor, or n is equal to the 0 vector. However, this has to be a unit vector. We're not allowed to have that equal to 0, so we can cross this possibility out. So the way to make this statement true is that the term in the parentheses is going to be equal to the 0 tensor. Then in that case, sigma minus sigma pi is equal to the 0 tensor. The determinant of two matrices or tensors that are equal to each other will be the same. So the determinant of sigma minus sigma p, we used lambda when we talked about strains, but sigma minus sigma pi, the determinant of that is the determinant of the 0 tensor, and the determinant of the 0 tensor is 0. So this is how we can develop our characteristic equation. It will be cubic in terms of the principal stresses. We can write this in the following form. Minus sigma sub p cubed plus I1 sigma sub p squared plus I2 sigma sub p plus I3 equal to 0, where I1, 2, and 3 are called invariants of the stress tensor. They can be listed here. I1 is the trace. We've talked about this with the strain tensor. The trace of the stress tensor is sigma kk. It's a summation of the diagonal terms. I2 can be written as 1/2 sigma ij minus sigma ii sigma kk. It's the sum of the determinants of the cofactor matrices, just like we did for strains. And then I3 is the determinant of that tensor. Now, one thing I want to point out here again, I think we did this when we talked about strains, is some books will alternate the signs of these terms and write these invariants in a slightly different way. So you may see somebody have a minus sign right here on the I2 term, and then the I2 term would be 1/2 sigma ii sigma kk minus sigma ij sigma ij. Just depends on which book you're looking at. So we should make a little note of that. In the characteristic equation, sometimes those signs alternate. Well, what we can do then is we can use that characteristic equation, solve the cubic for sigma p. We can get roots 1, 2, and 3, as we talked about. Corresponding to each of those roots are 3 eigenvectors. Those 3 eigenvectors, by the nature of there being an eigenvalue problem, are going to be mutually perpendicular to each other. And so we can define directions in space in which we can reorient that cube such that we have all and only normal stresses, all perpendicular to each other in some particular orientation. As we talked about for the strain problem, I won't go into great detail on solving the three-dimensional problem. You can use MATLAB, you can use there are places on the web that you can type in numbers of your matrix and end up with the principal stresses, 3 values. On a quiz in my class, we will take and have a reduced order stress tensor for generalized plane stress, in which one of the eigenvalues will be very easy to find, and then the other 2 eigenvalues can be found by simply working with a 2x2 matrix, which is pretty straightforward. So the stress eigenvalue problem will be similarly solved to the strain eigenvalue problem. Finally, we can note that we want the eigenvectors to be unit vectors. So that the identity n1 squared plus n2 squared plus n3 squared will hold, equal to 1 will hold. Now there are a lot of implications about this eigenvalue problem that we'll dig into as we go through more examples and other aspects. One of the things that we'll see is that there's a relationship among the principal stresses and local maximum shearing stresses in between 45 degrees in between the principal stress or eigenvector locations. And so that's explained in a little bit more detail in our book. Like I said, we will kind of take this up as it comes along. So I think as kind of a bite-sized portion of this lecture, I think this is good. But we will again explore what it means to solve the eigenvalue problem in additional examples and a little bit later in different lectures.